Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
This problem asks us to figure out the magnetic moment of a small conducting charged sphere that is being rotated around with an axle. So let's just get an idea of what's going on in this problem. So we have this charged sphere here. It's going to be connected to an insulating rod, and then this rod is going to be rotating around with a given angular velocity. Let's say it rotates around like this way, and we have an angular velocity that's given as 150 radians per second. So this charged sphere, this sphere that has charge q, is basically going to be mapping out a circular path around this of a radius that is the length of the rod, right? Now, if you remember the definition of the magnetic moment, it's going to be derived is if we have a current going through a loop like so, and it could be a coil or such with many turns like this. The magnetic moment of such a thing, let me get rid of this. Magnetic moment of such a thing is given by how many turns multiplied by that current that's going through, and then multiplied by the surface area of the path that the cross-sectional path that the current is mapping out, right? So it could actually be something even more complicated like this, right? The current's going around in that direction, but whatever this cross-sectional area would be, that would be the A we put in the magnetic moment. But it's much easier in this problem, right? We see that the type of path that this charged sphere is mapping out is just a circle. So the cross-sectional area is going to be given by pi r squared or pi l squared, L being the length of this rod here. Now, when we have to think about a magnetic moment, right, we want to have a current, but we're only given the charge of this thing. So how the heck do we turn that into a current? Well, if you think about it, this charge of Q naught is going around in a circle for every single period, right? So this charge is actually going around per unit time. So that actually gives us a current, right? The definition of current is how much charge goes by per unit time, right? So because we know how fast this is rotating at a constant velocity, we know how long it takes to go around one time, and we know how much charge goes around one time. It's the charge placed on this small conducting sphere. So if we want to figure out the current going through this loop here, we just take the charge that goes through, which is Q naught, divided by how long it takes to go on once, and that is a period, right? And we know for something rotating at an omega, the period, the time it takes to go around once, is given by, well, how many radians are in a whole circle? 2 pi. And then we divide that by omega. So we see that gives us how long it takes to go around once. So, what does the expression for our magnetic moment look like? Let's write that out. Down here, magnetic moment is the number of turns. It's just one, so we'll leave that out. It's the current multiplied by the cross-sectional area of this path. The current is given by our charge that goes around once per period, and the area is given by the area of the circle, pi l squared. Well, L, right, again, is the length of the rod. Now, we just saw that the period, the time it takes to go around, is 2 pi divided by omega. Well, if our period is in the denominator, then we can multiply by the reciprocal and get the same thing. So we have Q naught, and we're going to multiply by omega, divide by 2 pi, and then multiply by our pi l squared. We see our pi's cancel, and we get an expression of Q naught times omega times L squared, all divided by 2. Now, again, I have left myself with not quite as much room, so if I plug all these values in, I have, 0.4 times 10 to the negative 6 coulombs for the charge. The length of the rod is 0.2 meters. Like I said before, we're going at around at 150 radians per second. And of course, 2 is just 2. We plug all these things into our calculator, and we see that the magnetic moment created by this situation is actually going to be 1.2 times 10 to the negative 5 amps times meters squared. Let me write that meters a little better. Amps times meters squared. And that is our answer.